Alright, hi guys, sorry I couldn't be there today. We're going to wrap up our notes on trigonometric equations from lesson 6.5 with our day 3 notes here. We're going to do a little bit more intensive stuff today, so we're going to take our time going through these examples. Make sure you do go ahead and take notes on this, as it will be a little bit more challenging than it has been the past couple of days here. So we're going to solve trigonometric equations that use quadratics, and we're going to use identities to help us solve those trigonometric equations. So we're going to start by first of all reading our directions very carefully. The directions here are solve the equation on the interval 0 to 2 pi. Remember, when it says on the interval, we don't have to worry about adding that 2n pi. So we're going to start with example 1 here, which is 2 sine squared of x minus 3 sine of x plus 1 is equal to 0. What I want you to notice in this problem is that we have a quadratic. Remember, what makes it quadratic? Well, we have a squared here. So we're going to go ahead and we're going to try to solve this using one of our methods that we've used all the way since Algebra 1, which is factoring. And these will factor pretty nicely for the most part. So when we take a look at this quadratic here, I'm going to try to factor it. I could go ahead and use MAF, or whatever you need to do. If in the meantime you don't want to think about this as 2 sine squared of x minus 3 sine of x plus 1, remember that u substitution we did, where you can let u equal the thing you don't like. So for example, this could be considered the same thing as u being equivalent to the sine of x. So this is 2u squared minus 3u plus 1 equal to 0. And so you could go ahead and MAF, or if you could just look at it, that's good as well. And we're going to go ahead and factor that. What it ends up being when we resubstitute sine of x for u is it turns out to be a 2 sine of x minus 1 times sine of x minus 1 equal to 0. So now that we've factored it, we use the zero factor property to set each of these factors to 0 and solve. So you're going to set 2 sine of x minus 1 to 0, and you're going to set sine of x minus 1 to 0, and solve just like we've done on the previous days. So really, the only thing that's a little bit more challenging so far in today's lesson is the fact that we had to go ahead and take a look at this step up here. We had to factor it. And I don't want you thinking of the factoring as anything too crazy. So we'll go ahead and we'll solve this. So I end up with sine of x is equal to 1/2. And sine of x is equal to 1. All we have to do is look under a unit circle, remember, because we're only looking for solutions on the interval 0 to 2 pi, including 0 but not including 2 pi. So if we look on our unit circle to find the sine of x equal to 1/2, you should find 2 places where that is true. So there's 2 places where the y-coordinate is 1/2, and that turns out to be at pi over 6 and 5 pi over 6. Then we look on our unit circle where our y value is equal to 1, where sine of x is equal to 1, and that's only at one place, which is pi over 2. So we're going to go ahead and list our answers. We try to put them smallest to biggest. Pi over 6, pi over 2, and 5 pi over 6. Alright, moving on to example 2. Once again, you should be noticing right away in this problem that we have a quadratic. Okay, remember the quadratic here is because we have that squared. Now, as far as factoring goes, we should always look for a GCF. There isn't one. Then we see if we have a binomial here. Can we do the difference of squares? Nope, because of that 3. The 3 is now a perfect square. It's not a difference of cubes. So how do we go ahead and solve this? So although factoring is a great resource for us, remember factoring is not the only way you can solve a quadratic equation. We can also solve just with SADMAP. Anytime you can do that, you should go ahead and try it. So for this one, we definitely can. Remember, who can I subtract or add over? I can add the 3. So I get 4 cosine squared of x is equal to 3. Who can I divide or multiply by? 4. So I've got cosine squared of x is equal to 3/4. And then I'll take care of the exponent. So I'll get rid of that squared by taking the square root. Now this is where you have to be very careful. Remember, whenever you solve an equation by taking the square root, you have to remember to put down your plus or minus. So this is equal to plus or minus the square root of 3, which I can't do, all over the square root of 4, which is 2. So now I have to look on my unit circle. Where are my cosine or my x values equal to positive root 3 over 2 or negative root 3 over 2? And we get the following locations. So we get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And remember, those are our only solutions because we're only on the interval 0 to 2 pi. Remember, if you guys are falling a little bit behind here, you can always kindly ask the sub to please hit the pause button. Alright, let's try example 3, same directions. We're solving on the interval 0 to 2 pi. Now this one, example 3, sine of x tangent of x is equal to sine of x. A lot of people want to go ahead and divide by sine of x, and I wouldn't fault you on that logic. You would want to get rid of it, but the problem is you can't. The reason you can't do that is if you divide both sides by the sine of x, you're eliminating it. And by eliminating it, you're taking away where some of our solutions or some of our roots lie. So instead, what we have to do here is we're going to get this set to 0. So sine of x tangent of x is equal to sine of x. Let's get this set to 0. So I have sine of x tangent of x minus sine of x is equal to 0. And while this is not a quadratic, we can solve it by factoring because we have a GCF of sine of x. Now if we had decided to divide it out instead of factor it out like we did here, we would have taken away essentially 2 solutions to this problem because you still would have had your tangent of x minus 1 equal to 0, which we'll go ahead and solve here. But what you would have missed out on is that we need to set sine of x equal to 0 as well. So I can go ahead and I'll get my tangent equal to 1. And you have to be a little bit more careful, of course, where the tangent is equal to positive 1. That's going to happen at 2 places, at pi over 4 and at 5 pi over 4. Remember, if you don't believe me, you can go ahead and take your y-coordinate divided by your x-coordinate, and it should turn out to be positive 1. Now over here, when we have the sine of x is equal to 0, where is our y-coordinate equal to 0? Well, it's equal to 0 at 2 places that we can count, 0 and pi. Remember, 2 pi does not count because we have this parenthesis here. So 2 pi is not part of the interval we're looking at. It's not included. So my final solution here would be 0, pi over 4, pi, and 5 pi over 4. Alright, so I want you to go ahead and you could try cosine of x is equal to 2 sine of x cosine of x using that same logic we just used in example 3. So go ahead, please hit the pause key. Give us a couple minutes here for everyone to work this out. And when you come back, check out your answer and see if it turns out to be good. Alright, if you guys did not get the answers that I have boxed off here, you can hit the pause key again to look back at all the solutions I have and write it down in your notes. Otherwise, we're going to move on to our next example. Alright, so now the directions are a little bit more intense for us because if we take a look at it, what we get to do is use a trig identity to solve the equation. Remember, once again, we're on an interval from 0 to 2 pi, so we don't have to worry about adding that 2n pi or 1n pi to it. So we're going to go ahead and we look at this. We have 2 sine squared of x minus 3 cosine of x is 0. Now we can try to do what we've been doing in the past few examples here, which is to go ahead and try to factor it. Is there anything that I can factor here? Well, the problem is there's no GCF, and on top of that, we're dealing with sines mixed with cosines. So we've used this strategy before when verifying trig identities. If we want to go ahead, let's try to get this all in terms of the same thing. So for example, let's either try to get it all in terms of sines or all in terms of cosines. Because I see this sine squared, I'm going to go ahead and use the Pythagorean identity to substitute the fact that sine squared plus cosine squared is equal to 1. Therefore, I can replace sine squared with 1 minus cosine squared. So what I have here is 2 times 1 minus cosine squared of x minus 3 cosine of x is equal to 0. I'll go ahead and distribute that 2. And I'm going to kind of do a couple of things here. I'm going to distribute the 2, but I'm also going to rearrange this. So I've got 2 times negative cosine squared, which is negative 2 cosine squared of x. I still have my minus 3 cosine of x. And then over here I've got my 2 times 1, which is 2. So essentially I just put it in standard form from highest exponent to lowest exponent. Now when I factor this, I don't like it that I have a negative leading coefficient here. So what I'm going to do is I'm going to move everything over to the other side. So when I do that, I end up with 0 is equal to 2 cosine squared of x plus 3 cosine of x minus 2. And now we have a problem like what we began with today, where I can go ahead and factor that. I could use MAF, and I could do some u substitution there, allowing u to be equal to the cosine of x. And when you go ahead and factor, you end up with 2 cosine of x. You get a cosine of x in our other. We're going to have a plus 2 here and a minus 1 here. And we can go ahead and use the zero factor property. So I can set 2 cosine of x minus 1 to 0 and cosine of x plus 2 equal to 0. And we're going to get some interesting stuff here. So over here, I get the cosine of x is equal to negative 2. I'm hoping that most of you are remembering that cosine has a range from negative 1 to 1. So can the cosine ever be equal to a negative 2? No, it's outside of the range. Therefore, that portion provides us with no solution. But we still have to check the other part. I'm going to add 1 and divide by 2 to get the cosine of x equal to 1/2. And when I solve that, I do get some solutions. I get pi over 3, and I get 5 pi over 3. And those are all the solutions to this equation. So just to kind of go back and recap, what did I do here? I started off by recognizing I couldn't factor anything. There was no GCF. They were in different terms. So I took sine squared and I replaced it using the Pythagorean identity with 1 minus cosine squared. Now in the next step, I kind of did two things at once. I distributed the 2, but in addition to distributing the 2, I also rearranged my terms. If you want to do that one step at a time, you're welcome to do so. After that, I recognized that I had a negative leading coefficient. So I don't like that, so I moved everything from the left side to the right side. So I added 2 cosine squared over, added 3 cosine, and I subtracted 2. Once I had this statement right here, I was able to factor. I factored, used the zero factor property, and was able to go from there. Alright, so once again, example 5, I'm using a trig identity. They're giving me this clue here to kind of separate it from things we've done in the past. The cosine of 2x plus the sine of x, we have no GCF, and the issue is we're dealing with two separate trig identities, or excuse me, two different trig functions. So we need to try to put them in terms of each other. So either changing the cosine to a sine or the sine to a cosine. I've said it before, anytime we have a double angle, I would highly suggest thinking about changing that. Now you should remember that the cosine of 2x had 3 options. We can replace that with the cosine squared of x minus the sine squared of x. We can replace that with 2 cosine squared of x minus 1. Or with 1 minus 2 sine squared of x. Well, if I want to replace it, and I can see that I have a sine of x over here, I'm going to choose the option that has just sine of x in it. So, as a result, I'm going to go ahead and choose the third identity. So I'm going to replace this cosine of 2x with 1 minus 2 sine squared. So I have 1 minus 2 sine squared of x. I still have my original plus sine of x equal to 0. Now I have a quadratic trig function, and if I look at it, it's not in standard form. I would really want this 1 to be at the end. But if I move that 1 to the end, I have a leading coefficient of a negative 2. I don't like that, so just like I did in the last problem, I'm going to move everything to the other side. When I do that, I get 0 is equal to positive 2 sine squared of x minus sine of x minus 1. And I can go ahead and factor that using MAF. I end up with my 2 sine of x, my sine of x, a minus 1 here, and a plus 1 here. Using my zero factor property, I set 2 sine of x plus 1 to 0, and I set sine of x minus 1 to 0. So when I solve, I get sine of x is 1, and I get sine of x is negative 1/2. Well, where do my solutions lie? My solutions lie at 7 pi over 6 and 11 pi over 6. And over here, sine of x is equal to 1 only at pi over 2. So my solution to this problem is pi over 2, 7 pi over 6, and 11 pi over 6. Remember, I try to put them in order from least to greatest. I know some of these are going to take you a little bit of time. That's why I'm not going to assign too much homework for you. Alright, I want you to once again go ahead, hit the pause key, and try this one out. 4 sine squared of x plus 4 cosine of x minus 5 is equal to 0. You're using trig identities here, and you should notice right away we've got an issue because there's no GCF amongst all three terms, and I'm dealing with a sine and a cosine. So you're going to want to do a trig substitution using an identity, and then factor to solve. Please hit the pause key now and come back when most students are ready. Okay, hopefully you had enough time to work this out. The answers are pi over 3 and 5 pi over 3. Taking a look, I substituted for sine squared using the Pythagorean identity. I set it equal to 1 minus cosine squared. I distributed the 4 to get this line right here. And I was about to combine my like terms, but I already recognized that would leave me with a negative first term. My quadratic term would be negative, so I moved everything to the right and combined like terms here. Then you can factor with MAF, and what you notice is you have identical factors. So I don't have to set them both to 0 because we know they're going to make the same answer. And those answers turned out to be pi over 3 and 5 pi over 3. Alright, example 6, we have cosine of x minus the sine of x is equal to negative 1. Now I consider this one to be a little bit more tricky, because if we try to apply what we had been doing before, it's not going to work here. There's nothing to factor. I mean, what can I do with cosine and sine? I can't really substitute anything. There's no Pythagorean, reciprocal, quotient. So I'm kind of stuck. So we're going to do something we haven't done before. So it's kind of a last-ditch effort. So I'm going to call this our last-ditch effort. And what we're going to do is we're going to actually square both sides. Now I need you to recognize how I'm squaring both sides. I'm squaring the left side together and the right side together. So what this really means is I'm going to do the cosine of x minus the sine of x times the cosine of x minus the sine of x equal to negative 1 squared. Well, remember, negative 1 squared is positive 1. And you're probably going right now, we've made nothing better. But let's go ahead and we can FOIL this. Remember, we have to FOIL, we can't just FL. I get cosine squared of x minus cosine of x sine of x minus another cosine of x sine of x plus sine squared of x is equal to 1. Let's go ahead and we can clean this up a little bit. We've got cosine squared of x minus, these are like terms, so that works out to be 2 cosine of x sine of x plus sine squared of x equal to 1. And I think a lot of you at this point are recognizing we have a couple of our favorite things here. Cosine squared plus sine squared are Pythagorean identity. So I can wipe those out and replace that with a 1. I still have my minus 2 cosine of x sine of x. So now let's go ahead and let's try to solve here. I'm going to subtract the 1 over. So I get negative 2 cosine of x sine of x is equal to 0. Hey, we can actually now use our zero factor property, because we have a couple things multiplying together and they're set equal to 0. I don't need to worry about the negative 2. If it really bothers you a lot, you can divide it out. And so we have cosine of x sine of x is equal to 0. So we need to set the cosine of x to 0 and the sine of x equal to 0 and solve. So where's the cosine equal to 0? Well, that's going to happen at pi over 2 and at 3 pi over 2. Where's the sine equal to 0 at? At 0 and pi. Remember, 2 pi isn't going to count because we're not including 2 pi in the solution. It's everything up until that point. So our answers here are 0, pi over 2, pi, and 3 pi over 2. So that's another strategy to have up your sleeve. If you can't factor, there's nothing to do there. You can't solve with SADMAP because we've got 2 different trig functions in here, 2 unknowns. A last-ditch effort, the idea is square both sides and invoke a Pythagorean identity. So I want you to try this one. Try to be unique. Try to think it out. Cosine of 2x is equal to the sine of x. Try it out and come back to me and see how you did. And so as you can see, we end up with 3 solutions: pi over 6, 5 pi over 6, and 3 pi over 2. This one was not as tricky as the last one, so I don't want you thinking that they all have to go to that degree of difficulty. So we get our 3 solutions by using one of our double angle formulas. Why did I select to choose 1 minus 2 sine squared? Well, I saw on the other side I had sine, and I wanted to make sure we kept them all in the same trig identity. So instead of choosing cosine squared minus sine squared, which would have included a cosine and a sine, or 2 cosine squared minus 1, which once again would have mixed me up with a sine and a cosine, I chose 1 minus 2 sine squared, got it set to 0, factored, and got our solutions. Now, if you're not understanding all of this, or if you think you need to watch this video again, I am going to post it on Schoology. So it will be on Schoology for you to view again. So you're allowed to go ahead and go back and look at that. For the rest of class today and your homework tonight, you're supposed to use your textbook to do the following problems. Page 637, numbers 39 to 79, every other odd.